Hello friends, welcome to your channel Aarohi Classes, and today's lecture topic is polarization of the electromagnetic wave. So first we will discuss the definition. The path traced by the electric field vector of electromagnetic wave decide the polarization of the electromagnetic wave, and the antenna transmitting and receiving such electromagnetic wave is said to have such polarization. Okay, so the definition is the path traced by the tip of the electric field vector of EM wave decide the polarization of the EM wave, and the antenna transmitting and receiving such waves is said to have such polarization property. Such polarization properties. One component of the electric field vector produce only the linear polarization along the direction of that component. Okay, one component of electric field vector produces only the linear polarization along the direction of that component. Okay. See, this is the wave which is propagating along one direction. This is X. So you can see here the variation of electric field. The variation of electric field is along X direction only. You can see here pi by 2 omega, pi by 3 pi by 2 omega. Okay, so you can see here this is the electric field variation. The electric field variation is along only in X direction. Okay, E field variation. E field variation. So at Z equal to 0, Ex equal to x hat E naught cos omega t plus phi. So we can say this is x directed linear polarized wave. Two component of electric field two components of electric fields may produce number 1 linear polarization, number 2 circular polarization, and number 3 elliptical polarization. Elliptical polarization. Okay, so first we take linear polarization case. Linear polarization. Two component two components of sinusoidally time varying field having any amplitude but same phase will produce only linear polarized wave. Okay, two components of sinusoidally time varying field having any amplitude but same phase will produce only linear polarized wave. You can see here we have two components of electric field F1 and F2. One is along x direction cos omega t plus phi. F2 it is along y direction cos omega t plus phi. You can see here both have different magnitude but the phase is same. There is no any phase change between F1 and F2. Okay, so we have to find the magnitude and angle. So mod of F will be equal to under root F1 square plus F2 square this is F1, this is F2, and this is the angle, and this is final F. So mod of F equal to under root F1 square plus F2 square, and alpha equal to tan inverse F2 divided by F1. Okay, so you can see here alpha is the direction of polarization. Direction of polarization. which is independent of time. Means as the time passes your alpha will remain constant. Okay, alpha is not changing with respect to time. That means your polarization is fixed and it is linear. Any number of linear polarized vector having different direction and amplitude but are in phase is also a linear polarized vector. Okay, suppose we have more than two vectors having different magnitude and direction, but the phase is same, there is no any phase change, all are in the same phase, then they will produce a linear polarized wave. Okay, any number of linear polarized vectors having different directions and amplitudes but are in phase is also a linear polarized vector. The next is circular polarization. The two electric field components time varying when meet the following condition will produce circular polarization: equal amplitude, space quadrature and phase quadrature. Okay, so write down two electric field components bracket time varying when meet the following condition will produce circular polarization. Number 1, equal amplitude. Number 2, space quadrature. Number 3, phase quadrature. Equal amplitude, space quadrature means if one component is along x direction, then another component should be in y direction. There should be space quadrature. And phase quadrature means there should be 90-degree phase difference between two waves. So see here, F1 which is along x directed having magnitude E naught F naught cos omega t plus phi. F2 is along y direction, magnitude is same f naught, and there is a 90-degree phase shift plus pi by 2. So see here, in these two components we have all these conditions satisfied: equal amplitude, space quadrature, one is along x direction directed, another is along y direction, so second condition is also fulfilled, and phase quadrature, there is a 90-degree phase difference between these two, so third condition is also fulfilled. So resultant final vector will be equal to f1 plus f2. Magnitude of f final will be equal to f naught. Okay, you can write here f naught. And angle of polarization alpha equal to tan inverse f2 by f1. So it will come f naught cos omega t plus phi plus pi by 2. So cos 90 plus theta, cos 90 plus theta is equal to sin theta, sin omega t plus phi, and f naught cos omega t plus phi. F naught cancel out, and this will become tan omega t plus phi. Finally alpha will be equal to omega t plus phi. Now you can see here alpha is a function of time. In previous case, in case of linear polarization, alpha is not a function of time, but in this case alpha is a function of time. So the electric field, final electric field of magnitude f naught is rotating, and magnitude is f naught. The electric vector of magnitude f naught is rotating with angular frequency omega, forming a circular path. Okay, so you can see here alpha is the angle of polarization, so the resultant f naught, resultant electric field vector, is rotating along a circular path with angular frequency of omega, forming a circle. Because amplitude is same, so it is forming a circle. So this is circular polarization. So we can write here the electric vector of magnitude f naught is rotating with angular frequency omega, forming a circular path. So this is all about circular polarization. The next is elliptical polarization. Now this, if two components have different phase, okay, different phase means not 90-degree, other than 90-degree, and magnitude is also not equal, okay, equal to each other, then the polarization is elliptical polarization. If the magnitude not same and phase difference is also not equal to 90-degree, then the wave have elliptical polarization. You can see here Ex equal to x hat E1 sine omega t minus beta z. This is x directed wave, and Ey equal to y hat E2 sine omega t minus beta z plus phi. Okay, now see in this case both amplitude are different, E1 and E2, and you can see here there is a phase difference phi which is not equal to 90 degree, and the wave is moving along z direction. The wave is moving along z direction. The combined instantaneous field is equal to I E1 sine omega t minus beta z plus j E2 sine omega t minus beta z plus phi at z equal to 0, Ex equal to E1 sine omega t, and from this we can find the value of cos omega t. Cos omega t will be equal to under root 1 minus Ex divided by E1 whole square. Ey equal to E2 sine omega t cos phi plus cos omega t sine phi. We will expand this. Okay, Ey equal to E2 sine omega t plus phi at z equal to 0. So we can expand sine a plus b, sine a cos b plus cos a sine b. Now we will put these two values in this equation and we will get elliptical polarization equation. E divided by E2 whole square equal to Ex divided by E1 whole square plus 2 E1 Ex Ey divided by E1 E2 cos phi plus sin square phi, or a Ex square minus b Ex Ey plus c Ey square equal to 1. When we compare both equation, we can find a equal to 1 divided by E1 square sin square phi, b equal to 2 cos phi divided by E1 E2 sin square phi, c equal to 1 divided by E2 square sin square phi. Above is the equation of ellipse. This figure shows the trace of the ellipse where OA is the major axis, OB is the minor axis, and tau is the tilt angle. Okay, so after solving Major axis OA is given by major axis OA is OA equal to half EX square plus EY square plus bracket EX to the 4 plus EY to the power 4 plus 2 EX square EY square cos 2 phi power half whole power half. Similarly, minor axis OB equal to half EX square plus EY square minus EX to the power 4 plus EY to the power 4 plus 2 EX square EY square cos 2 phi power half whole power half, and the tilt angle of the ellipse with respect to x-axis. Tilt angle of ellipse with respect to x-axis equal to half tan inverse 2 EX EY divided by EX square plus EY square cos phi. 4 E1 equal to 0. If one of the wave is 0, final wave is linear polarized EX. If EX equal to 0, wave is linear polarized in Y direction. If EY equal to 0, wave is linear polarized in X direction. 4 EX equal to EY and phi equal to 0 in phase. Gamma equal to 45 degree. Linear polarized wave. If phase is 0, if phase difference is 0 and the magnitude are same, then the wave is linear polarized, but the angle of polarization is 45 degree. Linear polarized wave in 45 degree direction with respect to X direction. 4 EX equal to EY and phi equal to plus minus 90 degree. The wave is circular polarized. The wave is circular polarized. 4 phi equal to 90 degree. from receiving point of view, if phi is 90 degree, okay, plus 90 means anti-clockwise. From the receiving point of view, the wave is moving in anti-clockwise direction, and this wave is known as right hand circular polarization. Okay, suppose we are standing here in front of this and the wave is rotating in anti-clockwise direction, then this wave is known as right hand circular polarization. If the wave is rotating clockwise direction, okay, if the wave is rotating in clockwise direction, or you can say phi equal to minus 90 degree, then the wave is left hand circular polarization. At the receiving point of view. Okay, so this is all about polarization. If you like my video, please subscribe my channel and share this video. Thank you.